Hello everyone. We have one presentation today, and presenter is Jeffrey Dylan Birch, and he's studying his bachelor's program in TTH, and he's doing computer science in 6th semester, and he's interested in systems programming, computer architecture, and embedded systems. And he'll discuss an interesting paper on accelerating graph neural networks in storage devices.
So yeah, as Rika said already, we're discussing a paper called BeaconGNN, large-scale GNN accelerator with out-of-order streaming and supercomputing. It's a very recent paper, which was released approximately like 2 months ago in the HPCA conference. Oh, it's not working. Nice. Okay, yeah, no remote, I guess. Oh, the PowerPoint is not focused. That's why. Okay. No, the PowerPoint was not in focus. That's good. Yeah. For the motivation behind this paper or this work, basically graph neural networks, or for short GNN, which we'll be using for the rest of the slides, is has been becoming more and more relevant in the recent years, especially because of social media analysis or pandemic predictions. They work on huge data sets, which are getting larger and larger by the year, and they have to basically deal with transfers between the host CPU and the storage. And the issue here is that PCI bandwidth is very small. A lot of transfers has to happen, and thus the the data path is basically a huge bottleneck for GNN trading. The paper, the goal of the paper is basically to improve data throughput for GNN training. And their key ideas is to implement your data processing across various levels in the SSD. Oh, sorry. Across multiple levels of the SSD. Two levels especially. First of all, the die level, where we try to reduce the bandwidth of the channels. And they also implement the channel router to reduce the firmware's workload. They also create a new data structure, which resembles the architecture of the SSDs more closely, and they try to use this data structure to enable out-of-order sampling. For the evaluation and experiments, they use an in-house simulator to evaluate the throughput, and the workloads are uploaded data sets by PyTorch, which resemble real-world data sets from various platforms like Amazon or Reddit or whatever. And they conclude in the end that BeaconGNN has a 11 times better throughput and a 4 times better energy efficiency compared to state-of-the-art ICs, which are used for GNN acceleration. First, we'll talk about the backgrounds, especially what even is a GNN, which I've already said is a graph neural network. They are very effective for working on data sets that describe complex relationships or dependencies between each node, which, for example, would be a social network or natural processing and natural language processing. You can basically split up the training stages in 2 stages. First, the data preparation stage, where nodes are sampled and feature vectors are fetched. And in the second stage, these feature vectors are aggregated and computed. Here's a very blurry image, but I couldn't find a better one. Basically, as an example of a graph neural network, in this case, a PageRank network for websites. It's also important to know how the SSD architecture actually works so we can improve on it. We also split it up again in front end and back end. The front end here consists of an embedded processor and a DRAM chip. Basically, they're there to run the firmware of the SSD. A DMA controller, which allows the data from the flash to be directly written to the DRAM without involving the embedded processor. And then two interfaces for each, the communication to the host via PCIe and the flash interface to connect to communicate with the backend. The backend is basically consistent of multiple channels, which contain multiple NAND chips. These are basically ordered in hierarchy, so each NAND chip contains 2 dies, which in turn contain multiple rows, which in turn contain multiple blocks, and then pages, which is the smallest granularity you can get. The pages are usually 4 kilobytes, and we will also later see in the simulator, they also assume the 4 kilobyte page size. Read operations are done on a page granular basis, and erase operations are done on a block granular basis. What is interesting, or what is also interesting, is that there's a new emerging technology called ultra low latency, or ULL for short. Basically, it just reduces the latency of the flash chips in the backend. And in this case, they use the Samsung Z-NAND SSD, and the ULL will also become relevant to their new solution for GNN acceleration. You also need to understand how the I/O processing actually works to understand what the challenges behind the accelerations are. First of all, the firmware is running only on hardware threads, which are usually 2 to 4. What it's essentially running is an I/O poller, which pulls the I/O, which is basically pulling I/O requests from the host. A flash translation layer to translate logical page addresses to physical page addresses, which is kept in DRAM, and a flash I/O scheduler, which is there to send the requests to the flash backend. To process a single I/O request, first the I/O poller gets the request from the host, which is usually put in a ring buffer. Then we do a page lookup from the logical page address to the physical page address. With the physical page address, we can then query for the page we want to the flash via the I/O poller. And after the page is fetched and put into DRAM, we can fetch it from the DRAM and then send it to the host memory again by DMA. And thus, and also the I/O poller then notifies the host that the transaction has been done. Then to the motivation of this paper for why we're even considering ISC. As I said, the data sets have become larger and larger in the factors of hundreds or even multiple terabytes. The issue here is that we cannot fit this anymore in system memory because of the architecture imposed, the max capacities imposed by CPU architectures or motherboard architectures. Though they can easily fit in single SSDs, and SSDs are also generally cheaper than DIMMs. A common technique to fetch nodes and feature vectors from graphs is graph stage, which stands for graph sample aggregation. The key idea behind graph stage is mini batch processing, where we just select a certain amount of target nodes and also only generate subgraphs of the entire network, which means we only look at the local view of the network and not on a global view, so we can reduce data transfers. We also sample the neighbors only in subsets, so we don't need to worry about nodes with high amount of degrees. To compute the feature vectors, they use iterative message passing. For basically every hop, there's an iteration for feature computation aggregation. And for the process, again, what I said, we first generate the subgraph of each for each target node. We fetch a feature vector for the target, for the nodes and the neighbors. We compute k iterations of message passing for the k hops. And after the final iteration, we can just find the final embeddings, which we aggregated in target nodes and can basically send it back to the host. The core issues of GNN training is, first of all, interhop sampling barrier, which basically means that after each time we fetch a neighbor, we get the node ID, but the SSD doesn't know what to do with the node ID. So it would need to communicate back to the host to get a logical page address to fetch the next neighbor, which means after every hop, we need to communicate back to the host, and which gives us a great bottleneck in terms of PCIe transfers. The second problem is that the SSD only works on page granular transfers, which is not ideal because usually the data we work with is smaller than a page. So a lot of the bandwidth we use for the channels are essentially wasted. And there's also a lot of random and small I/O accesses, which means that the channel queues are filled to the brim, and parallelization between the dies on the same channel is basically impossible. And the third problem is that the firmware scheduled flash I/O significantly slows down every flash access because we have to read every read and write operation from the DRAM directly. And we also don't have enough hardware cores because the embedded CPUs usually only have 2 to 4 cores in each SSD. And there's also usually like hundreds of, like up to 100 channels per SSD. So we cannot fetch every, or like complete every I/O for every channel in the same cycle. And this is a problem because then we cannot keep up with ULL technology, or essentially the reduced latency of ULLs basically does not help us. Which is why they propose GNN to, first of all, they use other previous ISC works from previous papers to build up from there. The first key idea is to use glist, which basically is there to help us to compute the feature vectors. What they essentially do is embed an FPGA fabric inside of the SSD, which does the feature aggregation and computation. What they do with that is basically to eliminate PCIe traffic. The second work they heavily use is SmartStage, which is basically there to filter out nodes that are either like not relevant or basically useless for the calculations you want to do. They take these techniques and combine them into a 1.0 architecture. Basically, the host still controls the entirety of the GNN training tasks, and all the data-intensive operations are done inside the SSD. So the neighbor sampling, the feature table lookup, and the computations itself are done inside the SSD, and the host only has to fetch the results. The neighbor list, again, is filtered by SmartStage, and glist is there to basically enable us the in-storage computations. Though it still does not solve the challenges we mentioned previously. So they first, to solve the first challenge of the interhop barrier, they use direct graph, which is a new data structure. Direct graph is basically there to exploit the architecture of the SSD itself. Instead of using node IDs, it embeds the physical page address of the neighbor nodes directly inside the data structure. So what this basically enables for us is to eliminate the queries to the host to ask for the logical page addresses. So basically, the SSD knows directly where the next node is without needing to ask the host. The data structure is generally split up into primary and secondary pages, which are each also comprised into variable length sectors. The primary section stores metadata about the node itself, the feature vector, and also the length of the amount of degrees, basically, and also the neighbor offsets in the SSD. And if there's not enough space in the primary section, we can use a secondary section where we keep the rest of the neighboring nodes. And then the secondary section is referenced in the primary section. Here would be a representation. Again, as you can see, here the secondary sections are referenced here for the nodes that didn't fit into the primary section. The metadata, the feature vectors, it's all basically there. And if there's sections that are smaller than pages, then we can just pack them together so we don't waste space. Essentially, what this enables us is that the host only needs to target the address of the target node, and everything else can be then done inside the SSD because we have the physical pages directly. The second optimization is to basically solve the issue of the channel bandwidth, and here they use a new data processing engine called the die-level sampler. It basically does the sampling procedure on the die itself. We employ two new registers, the GNN configuration register, which basically just contains the amount of hops we want to do and also the amount of neighbors we want to fetch. and a TRNG to random number generator, which is basically just there to uniformly and randomly decide which nodes we want to fetch. There's also two new commands, configuration and sample, though we're only interested in the sampling command. For the procedure, we first read the sampling command from the data register. Then we read the page that got fetched which is residing in cache register, and then we find the corresponding sector we're interested in. From the sector, we read the feature vector and the neighbors. We index into the neighbors with what I said previously with a true random number generator, and then they just they generate a new sampling command on the fly and write it in the data register again. So there's no need to communicate with the firmware. Basically, all the hops can be done in one go inside the die chip, and thus we also save a lot of bandwidth, and we reduce the transfers on the channels drastically. And the data is essentially then at the end put on the data bus. To alleviate challenge 3, to reduce the firmware workloads, there's also a channel level command router, which is basically at the bridge between the front end and the back end. The router basically runs a sampling command from the flash channels, because even if we generate the new commands, not all the commands can be done on the same die, because some neighbors can be on a different die. So we need to route them to the corresponding locations. For the procedure, we basically first parse the sample result we got previously. Then we identify the correct channel and then send the sampling command to the crossbar, to the correct channel. Then they send the feature vector to the DMA so they can be processed by the FPGA fabric. And they use a dispatch queue for each die per channel, so for the commands to be computed, and they use a round-robin issuer to issue those. So the overall architecture looks like this. We have a runtime, which basically takes customized NVMe commands, which can be used via IOCTL. It then submits the flash requests, and it also schedules the execution of the special accelerator, which we get from GLIS. The accelerator itself has a 1D array for feature aggregation and a 2D systolic array for general matrix multiplications. The flash die, as I said, is just there to sample the new vectors and generate new sample commands. And the flash interface, where the command level router lies, basically just puts the request to the corresponding correct channels and dies. For the evaluation, they evaluated multiple metrics, but we are only interested in 2 key metrics. But at first, the setup, basically, they compared 6 different systems. The first system is just a regular CPU-centric system where we have a regular CPU, a regular SSD, and they also use a DNN accelerator to basically accelerate the feature aggregation, which is what we would commonly see in today's GNN applications. Then they compared against GNN 1.0, which is supposed to be the state-of-the-art ISC from previous works. Then they include direct graph to see what impact direct graph has. Then they have a version where they only add the die level sampler. Then they have a version where they have the direct graph and the sampler, and then the full 2.0 setup. For the workload, as I said, they use real-world data sets from PyTorch Geometric. Here they used 5 of those, which are also used in the SmartSage paper back then. What is important to note here, though, is that they only use all 5 of those for the throughput analysis. After the throughput analysis, like the energy analysis, they only use Amazon for some reason. I mean, I will explain the reason later, but it's not a good reason. And for the performance modeling, they use an in-house simulator for the throughput analysis and Scalesim 2.0 to simulate the DNN accelerators. For the area and power estimation, they also use established software like MacPad and DRAM power. And for the near data processing elements, they just implemented them in HDL to be more exact Verilog, and then synthesize them and then analyze the areas which got produced. For the setup, they use a 4-core processor, a flash memory with 16 channels, 4 packages, and 2 dies. Here, again, they also use the common page size 4 kilobytes. They provide both the discrete accelerator for the CPU-centric configuration and the SD level accelerator for the Beacon 2.0 configuration. and both are also both are basically essentially systolic arrays. For the throughput, you can see that one of the biggest impacts this paper provides is the die-level sampler. Though with BG 2.0, it is not always consistently better than BGSP or BGSP. They don't give really an explanation why that is the case, but in general, you could say that at best they can get a 21.7x throughput compared to the CPU-centric configuration, and in the worst case, they only have a 10x increase. For the energy breakdown, they basically have two y-axes. The first y-axis is basically where basically energy was spent the most, and the other y-axis is the energy efficiency based on the CPU-centric configuration. So one would be the CPU-centric one, and even here we can see that the biggest increase or biggest jump came from including die-level sampler. Also interesting to notice that the DRAM usage got decreased by a lot, and that is due to the fact that we don't need to read and write a lot for the DRAM because the sampler samples multiple nodes at the same time. And yeah, what they conclude here is that BeaconGNN 2.0, that they basically improve the energy efficiency by tenfold. Important to note here that data is only for Amazon. They don't do it for any other workload. Then the data overhead, which is imposed by direct graph. Basically, the overhead is not that large, except for OGBN, and that is due to the fact that OGBN has a very low neighbor count for each node. But in general, you could say that the overhead is pretty negligible, and the direct graph is very applicable for most data sets. So they conclude essentially that BeaconGNN that it basically solves the problem of the interrupt barrier, then solving the channel utilization and the firmware workload. For the sampling order, what I said previously, the data structure basically enables the out-of-order execution. The die-level sampler then improves the channel transfer efficiency. The hardware accelerated routing reduces the workload of the firmware, and also the FPGA inside enables the computing and thus reduces the communication with the SSD and host over PCIe. They essentially conclude that BeaconGNN improves the GNN training task by 21.7 and the energy efficiency by 10x, only by increasing the area of by 1.26%. So to the strengths and weaknesses of the paper. First, near data processing seems to work pretty well here, especially the die-level sampler. And they also don't increase the area of the SSD that much. Especially the die-level sampler only increases the area by 0.1%. The usage of software-based solutions also makes it a bit cheaper to produce. If one would try to implement this hardware, it will be cheaper to produce. Because yeah, software doesn't cost anything. The paper provides a good explanation in why the challenges arise for the SSD architecture, and gives good background knowledge about how the SSD works. And they also use key ideas from previous works, which means they don't reinvent the wheel entirely and can also benefit from basically previous research. Biggest issues here, though, are that they cherry pick Amazon, and they do that on the basis of that they basically claim that Amazon is the most closely resembling data they have to the real world, but they don't give more explanation for this. The paper also doesn't provide any solutions for the high overhead you get for the OGBN dataset and direct graph. It also only focuses on ISC. They don't go that much into detail for processing in memory. Due to the implementation of direct graph, the SSD needs to allow the host to write to certain blocks directly to build up the graph itself, and that's a potential security risk because someone could technically just override the same flash chip over and over and over again to basically either destroy the hardware or do other malicious stuff. And in general, it only accelerates training, and training is done relatively infrequently. So one could ask if this work is worth it to do, or if this is more of a if it's even worth to do, since training is done relatively infrequently, and they don't mention how one would use this technology for data inference. And in general, the most damning evidence they have for the improvement is their throughput, and the throughput is measured using in-house simulators, which they don't provide a source for, or like any public source code, so we don't know how well it is implemented. And yeah, it could potentially muddy the data a bit. So at first, what I wanted to discuss here is the claim of OBGN with the overhead. Again, because of the low degree count, the overhead increases a lot, and they dismiss this kind of by saying that the densification law exists, which does work on graphs like that, for example, social media, where the nodes get higher and higher neighbor counts. But there are probably some models or workloads where the law doesn't apply, which maybe you can think of, or like which workloads or models would the densification law not apply, where the node counts will still keep low even after expanding the graph by a lot? Maybe in chemistry or traffic, if you can think of one idea. For chemistry, what I had in mind was molecular, where basically molecules are displayed as graphs, because molecules at most can only have 4 neighbors after each atom. So the densification law would not apply here. Or for traffic, where traffic systems, basically, when we look at the crossroads also does not really have that high of neighboring count. So the degree count will still not increase even after expanding the graph. For the second point I wanted to ask is, basically they're only discussing ISC, and the reasoning they give is that the DIMMs cannot exceed the maximum capacity of the data set they have. Though there is a technology called Compute Express Links, or CXL, where you could pool multiple DIMMs into one big pool, which is then accessed via PCI Express. So with CXL in mind, like, how would you maybe change this acceleration approach from IC to processing in memory? And maybe keep in mind that the DRAM latency is also significantly lower than the flash latency. So how would you implement GNN acceleration in terms of PIM when we have CXL as our backbone? Or maybe think about where would you maybe, instead of, because here they're doing it on a per SSD basis, and here we have multiple DIMMs. So maybe we could think about, okay, do we put the accelerators inside the CXL fabric itself, or do we do it on a per DIMM basis, or like what do you think would be the best way to do it? Or maybe do we do a shared IC and PIM solution, or?
I have one follow-up question.
Yeah. Or you can do, or just ask questions, that also works.
Yes, so CXL could maybe increase the system memory capacity, maximum capacity,
yes,
but will it cover all cases that ISC is covering, like in terms of graph size, I guess?
I mean, in terms of, because CXL basically allows to pool it. from the DIMM capacity is basically only mainly limited by the CPU and the mainboard. So if we use CXL, you could theoretically increase the size of the DIMMs by a lot. So it would be possible to store the graphs in there in terms of size. The only question here is because we have multiple DIMMs, where we would implement the processing nodes in the system. Like, would we do it on the CXL level where we combine everything, or do we do it on a per DIMM level? Or maybe it's also maybe we also need to think about, okay, we need to fetch the data, which is probably still residing in SSD, into the memory. How would we accelerate this? Like, what could we do here to maybe combine this together into one big technology? Because DRAM in the end is way faster than the flashes we have here in our SSDs. So yeah.
Okay. Well, I can think of some stuff, but maybe others. What was the SSD stuff for again?
In storage computing. So otherwise, if there's no ideas here, I will. There's also the aspect of why do we even do it on GNN? Because a lot of problems that GNN solves can also be solved with simpler models like convolutional neural networks, which are also way better understood compared to GNNs. Again, CNNs can also solve NLP problems, which GNN can also do. So the question is it even worth to accelerate GNN, since CNNs are way easier to implement and also to compute? But yeah, but we also have to keep in mind that that CNN only works on fixed grid data structures, whereas GNNs only allow where GNNs basically allow arbitrary data, which could be unsorted or nodes with different neighboring lists. So is it even worth to do it on GNN, or maybe should we just say scrap this and try to solve as many things as possible with other structures instead of graph neural networks?
I mean, I'm no expert on the difference between CNNs and GNNs, but the node, how you describe it, basically sounds like there's a strong motivation to actually do GNNs. I mean, irregular structures is probably what you work with the most in like real world scenarios or in complex models, etc. So it sounds like still a strong motivation to follow, even if there are ways of reducing the actual problem domains to a big split of data. It might be still more accurate to work with GNNs.
Could you maybe think of one problem that can definitely not be solved with, like, because for example, CNN only works on where we know the input size very well, which is fixed. Could you maybe think of something that's only solvable with GNN? Just as an example, or anyone else.
Like because social networks suggest information form like this, and then like
yes, for example, yeah, social networks or web page ranking, or yeah. I mean, even natural language processing, you could argue that the input size is not uniform because you still have variable sentence lengths. So yeah.
How does this apply to natural language processing? Like, where is the graph structure?
It's basically where because the way I work with NLPs before with convolutional networks is because you could get embeddings for each token, right? And if you only have a fixed input, you have to somehow combine these tokens into a fixed input because sentences are variable length. So so for CNNs, you would need to data pool those together, for example, with a mean function. And here you would be able to basically combine you have, for example, have a text with tokens, and you draw the relationships. If you have like a large text and then you want to draw the relationships between each token, because most tokens will probably appear multiple times in text, right? So you could probably make a graph where you show a relationship between each token inside the whole text, where you don't have to basically data pool them together, because data pooling in the sense gives us like a loss of information if you use it on CNNs. Is there, in general, any questions to the whole technology, or maybe the problem statement, or anything else?
Not the accuracy of GNNs, and to be honest, it's dependent on the way you train it.
I mean, depends on the problem, but yeah, in what again, in natural language processing, since if you have a fixed size, you would need to aggregate, like you would need to have each embedding for the token, right? And you would probably need to do it on a per sentence basis instead. So you would data pool them together, and the data pooling itself will probably reduce the accuracy, but like the details inside of the sentence. And with GNN, you would not need to do this, so you keep the picture a bit more clear. So yeah, it would probably be more accurate using GNNs instead of CNNs. There's also a paper that analyzes the accuracies between GCNs, which is graph convolutional networks, which is mostly used for image processing, compared to CNNs. And it also suggests that GCNs are also outperforming CNNs in terms of accuracy, but they're just computationally way more intense. So yeah, one could also ask, maybe improve CNNs instead, like in terms of the theory, or yeah, it's more of a trade-off between computational complexity and accuracy.
I maybe got a bit lost, so I'm just trying to answer that.
Yeah.
So like in the traditional existing solutions, the entire graph would be stored on the SSD, but like to process it, it would have to be loaded into RAM, but it doesn't fit entirely into RAM. So like there's a lot of traffic.
Yeah.
And so here you got processing in the SSD.
Yes, basically you have the host basically only orchestrates. Basically, you tell the CPU, hey, I'm interested in this, and this node. The CPU then tells this to the SSD, which is to the modified SSD with a customized command. And the SSD then does all the training around this target node, the aggregation, everything, and then just sends back the result.
Okay. And I think in one of your strengths, you mentioned that it's like a software-based solution. What does that mean? Like, you still need to do hardware change for this?
What I meant is that not everything is done in hardware. That some solutions are done in software, when I started reading the paper, I didn't expect like them to also have software-based solutions in there, like changing the data structure of the graph.
I see.
Yeah. Otherwise, if there are no other questions, I think I will conclude this presentation. Thanks for listening and engaging, and yeah.
Is it over?
There's no presentation anymore, yeah.
Yeah,
Unless you want to present them.
no, it's okay. I would rather listen to you present some.
We can.